Hello, welcome to CN Videos, a YouTube channel where we try to help you get started with modeling. And also, if you're already down the modeling route, we also aim to help you curate an effective solution for whatever computational modeling challenge that you may be dealing with. My name is Dr. Michael Okereke, and I'm making this video that has been widely requested by viewers in this channel that keep asking for a Monte Carlo style implementation where you generate randomness within a microstructure. So the object of this video is how to generate random inclusions within a finite element domain. So let's sit back and relax as we go and get started with modeling. As we get started with modeling, and I want to look at practical scenarios, and the first thing is snowflakes. So when snowflakes are falling, do you wonder how they fall? What is the reasons why they fall in the pattern that they're falling? Is it a very random process? Probably yes, it is a very random process. And this is one of the processes that is real life, and if you're ever trying to model the positions and the distribution of a snowflake, then the method that we're describing in this video will essentially be important for you. The next thing is the stock market. When you consider what's happening in the stock market, it's quite a very random, chaotic environment. You don't really know what's happening to businesses. And so that again is a random process. Again, something that the approach that is being described in this video will be essential in understanding that. And then the final case is when you think about traffic. It's always not very easy to understand what's going to happen with the traffic. Again, it's a random situation. And so what we see with this traffic scenario, again, is something that will be adaptable to the process that is being described in this video. But obviously, our interest is when we are looking at material behavior. Okay, material behavior. Many of the viewers on this channel are interested in material behavior. And so the idea here is we want to generate randomness within a material behavior. And so a researcher can ask himself, how can I realistically create random distribution of particles within a material domain? And this is against you trying to be deterministic in the way you do this. So you choose positions and you begin to lay the particles in there. You want the system by itself to be able to create this randomness, and when those randoms are generated, they should ideally reflect what you see in reality. And so that's the objective of what we're trying to do with this video. And I want to start with a representative volume element of that kind of broad process that you're looking at. And this is an RVE that has a random distribution of particles, of different types, of different colors. Some of them are big particles, some of them smaller particles. And we should, in a way, be able to recreate the system. And the question the researcher would be asking is, how can I actually do this? Is it something that I can easily do? How possible can I do? How do I know that whatever I'm generating will be the right kind of representation for the domain I'm interested in? And the answer lies in a very powerful method, which is called the Monte Carlo Methods, or the Monte Carlo simulation. So this is something that is very common in science. And maybe some of you that are viewing this video, maybe you already have exposure to Monte Carlo. It applies to many areas of life because it's really about modeling real life systems in their randomness, in their chaotic behavior. So Monte Carlo method is at the core of the approach that you will need to use to generate this random particle distribution within whatever FEM infrastructure that you're trying to use. And so to look more closely on that, I found this paper that was published in 2014, slightly old paper, that De Croze and his team published this paper, and they were looking at this question of why the Monte Carlo method is still important today. And I want to quote the very first introduction, the first thing they say in the introduction, because I think it captures the object of what we're trying to look at today. And it says that the Monte Carlo simulation is, in essence, generation of random objects and processes by means of a computer. And that's essentially what it is. So we want to use a computer to recreate the random behavior of snowflakes, the random behavior of traffic as it travels through the city, or the random, behavior of whatever randomness that you're interested in. And it's a computer-generated process. And it's not just about the objects. In material behavior that we're interested in this video, yes, it's objects that is being deposited in a defined domain. But that also will apply for processes like the stock market, processes like, traffic. and things like this. So these objects can arise naturally, like Deck is saying in this publication. It can also be artificial. You can create those artificial distribution of these particles. But this is what we want to be interested in as we look at this topic of the use of Monte Carlo method in generating randomness for a domain within a finite elements analysis scheme. And there are things that must be considered as examples of where this will happen. So what are the applications of this method? The first, I think, is when you're sampling real-life distributions. When life is happening, things happen in a very dynamic, realistic pattern, and there's a lot of randomness in them. So the Monte Carlo method is absolutely useful in trying to accomplish that. Then, of course, the second thing that we're interested in is the microstructure, recreation. If you're interested in creating microstructure, which is the kind of thing a lot of times, people within my area of research are interested in. How can I recreate microstructure in their reality, in how real life they appear? And so the Monte Carlo method will also be another useful way to do this. And the final case is when you're thinking of void formation within a structure, the positioning of those voids, their morphology, their size, their shape, the orientation, all that again are central to the Monte Carlo method. And this is the method that we're going to be using to do this. So a lot about the background on that. So the next thing I want to talk about is the implementation, the key steps of most Monte Carlo processes. And the interest here is within the area of finite element analysis. Of course, you can adapt this thinking for other industries or other areas of research. So the first step in the Monte Carlo implementation is what is called the hardcore model. The hardcore model, and this is about the random positioning of the fiber within the domain. And then the next step is what is also described as the periodicity of the material. So this is what I use to refer it. And I'm going to explain this a little bit more. And then the final method is a heuristic improvement on the originally generated model. So let's look a little bit more on these things. So the first of them is this hardcore model. And most Monte Carlo process will always have this hardcore model, which is at the core of the Monte Carlo process. And basically you've got a domain, and within that domain you start having particles randomly positioned within it. Whatever tool that you're trying to use, whether it's Excel or whether it's MATLAB or Python, whatever script, you must have a function called the rand function, the randomization function, because what this randomization function does is that it looks through the domain and start randomly picking positions for you in order to be able to find the locations where these particles will be. So whether it's, again, stock market you're trying to analyze, it introduces a random indicator or a random factor to prediction of what is happening in the stock. And that randomization is at the core of the Monte Carlo methods. It's not a real randomness, it's a computer-generated randomness, but that's what drives this idea of what's happening within this RV that we're interested in. And so you keep dropping into this RV environment, into this box or whatever, container that you're looking at, until you are not able to drop anymore, which is usually described as the jamming limit. But we'll talk a little bit more about that. Then the second step of that, because we are going to use this to run within a finite element scheme, probably use periodic boundary condition to analyze it, the next thing that we are interested in is this idea of the periodicity of the material. And that is the idea that if a material appears at one corner, then it needs to be duplicated at the other corner. So if you think about what we have here, so here we have a particle that has appeared on the other corner and then it's being replicated right away in this position. And you need to do the same for the other direction. So if we look at this case, we've got another particle that is appearing there and then it's being replicated on the top side. And I've got some more, again, another one that is here and other cases. So this periodicity of material is a bit of an artificial construct, but it's essential because you want to preserve the integrity of the particle within the domain. If you have half a particle that is cut off, it makes sense to replicate and create the other half at the other end of the domain. There may be instances where if you've got your particle that are appearing right at this corner, and then it becomes quite difficult to know, because then you have to replicate it at this corner, at that corner at the top, and all the four corners of the domain. This is both in 2D and in 3D. Okay, so periodicity of material is an essential process in having a representative volume element for the domain you're trying to analyze, especially if you're interested in using periodic boundary condition for your analysis. So that's the second step in the Monte Carlo method. And the third step is this heuristic improvement. There are different names people can call it, but I tend to use this word, a heuristic improvement. This is about, iteration on the original domain to make sure that it's able to take more particles basically within that domain. And how do we do that? So the first principle here is that the Monte Carlo method suffers from what you call a jamming limit. And that is the fact that you're dumping this particle in the domain. At a point during that dumping process, the particles get stuck. They are not able to. So if you ever try to put a lot of soccer balls within a bag, after a while it gets stuck. And so you need to then shake it in order for more to go in. So this is what also the Monte Carlo process suffers from. As you try to dump within the domain, particles stay in their position, and then it's difficult for new particles to take in. In fact, the jamming limit where this usually would happen is about 40 to 50%. So half of the domain is not able to receive more particles because of this idea of a jamming limit. So the classic Monte Carlo method, according to the hardcore model, always suffer from that. And so the next step, what we need to do is to apply a heuristic approach where you begin to shake the particles. So the idea here is that you shake or stir whatever container you're looking at. So whether it's an RVE system or a box, whatever, you stir it in order for more particles to come in. So the next step is to shake the container. So when you shake the container or stir container, whatever it is, the RVE gets stirred, and then that little shaking process will lead to more particles being distributed. So if you look in this case, right at the top end here, you have more particles that are now being available for you more spaces for you to put in more particles. And so this is what the heuristic process does. You try many processes until you get to the state where the system is actually able to take more particle. So those are the 3-step processes for accomplishing the idea of the Monte Carlo process. And for you to implement this, you need to write a code to accomplish these 3-step processes. But I have a code that I've written, which again, the link will be in the description for you to download and use. And this is a code that tries to implement these 3 things that we talk about. And that is the Monte Carlo Gen 2D. So I'm making a second video to describe exactly how this code works. So that video will be the second part of this first video, so that as you look at it, you can then understand how the implementation of the code that I've written actually works and how you can use it to solve whatever Monte Carlo problem you're trying to deal with within the area of material science. And so what is Monte Carlo Gen 2D? Basically, it's a MATLAB-based software for implementing these 3 steps of the Monte Carlo process that I've talked about, beginning with the random positioning of the fibers or the inclusions within the domain, which I call the hardcore model. And then the second state of it is the state where you're looking at periodicity of material. And then you get to a jamming limit where you're not able to take in more fibers. And so a kind of a stirring algorithm or a shaking algorithm, which is based on this heuristic approach, allows for more fibers to be dropped within the domain. So that's the third step. And the other thing that I've added to the code to make it easier for people within finite element is it generates the domain. It makes you to visualize. You can see the visualization of the model that you've generated. And then finally, it also creates Python scripts automatically for you to then run that Python script for abaqus, and then you get the result. Future versions of this code will look at doing the same with other finite element solvers. But for now, this first version is dealing solely with a 2D domain and for an abaqus infrastructure. Future releases hopefully will do that. So that's what the next set of video that I'm making about this will be about. And please do watch out for that video, and also do look at the links so that you'll see how you can download this code that we're interested in. And if this is the kind of video that you want to, please do subscribe to this channel and click the like button. The YouTube algorithm will continue to push this video to people. Put comments in the description section of what you think about this whole process, how you are going to be using the Monte Carlo method, if it's actually relevant for your area of research, and if there's any further kind of ideas or videos you'd like me to make, I'll be happy to hear them. Thank you for your interest in this channel, and see you in the next video. Bye bye.